Check your phone for a second. Imagine you unlock it tonight and find the exact same headline plastered across every single newspaper and screen on the planet. A single sentence humanity has been sweating out and waiting thousands of years to hear. We may have found life on another planet. For a few days in April of 2025, that wasn't a sci-fi prompt. It was our actual reality. An astronomer from Cambridge pointed the most advanced telescope ever built toward a massive rock called K2-18b, a world sitting 124 light-years away, buried in the constellation Leo. And right there, floating in its atmosphere, they detected a gas that, here on Earth, is manufactured by only one thing: living, breathing creatures. For a brief moment, it felt like the most monumental discovery in human history, and it led every news broadcast on Earth. It was the absolute smoking gun. And then, slowly, quietly, over the following months, the whole miracle began to rot. This is the real story of the planet that almost had life. How we found it, what we honestly thought we saw, and how science, doing the hardest, grit-tested, and most beautiful work it knows how to do, took the discovery apart, screw by screw, to find out if it was real or just a ghost in the machine. What is K2-18b? Why did the most exciting announcement in the history of astronomy completely evaporate? And what does this massive cliffhanger tell us about how close we actually are to answering the only question that has ever truly mattered? Welcome to Outbound. Let's go right back to the beginning. In 2015, a NASA telescope named Kepler was doing its usual nightly grind, staring at a small, cool, faint red dwarf star in the constellation Leo. Kepler was looking for microscopic dips in starlight, the tiny shadow a planet leaves behind when it passes right in front of its sun. And it caught one. A planet orbiting that red star every 33 days. They logged it as K2-18b. At first, it was just another cold serial number in a catalog that wouldn't stop growing. By the 2020s, astronomers had mapped out more than 5,000 planets outside our solar system, but the vast majority were dead, scorched earth graveyards, gas giants baking skin tight against their stars, frozen ice rocks in the deep dark, or worlds where the sky literally rains molten metal. But K2-18b had a massive wild card. It was sitting right inside the habitable zone, the Goldilocks zone. Not too hot, not too cold. The exact narrow orbital band where water can survive as a liquid. And liquid water, as far as we know, is the one non-negotiable threshold for life to happen. There was a catch, though. K2-18b looked absolutely nothing like Earth. It was massive, 8.5 times our weight, more than 2.5 times our size. Way too big to be a solid rocky world like ours, yet too small to be a pure gas ball like Neptune. It belonged to a freak class of planet that doesn't even exist in our own solar system. Astronomers call them sub-Neptunes. And here is the weirdest blind spot in modern space science. Sub-Neptunes are the single most common, abundant type of planet in the entire Milky Way galaxy. They are everywhere, by the billions, and yet we don't have a single example in our own backyard to study up close. We have small rocky worlds like Earth or Mars, and we have colossal gas giants like Jupiter or Saturn, but the planet that actually rules the galaxy is a complete stranger to us. K2-18b was the ultimate chance to understand a category of world we are, statistically speaking, completely surrounded by. For years, it just sat there in that massive gap in our textbook knowledge. Too big, too weird, too far away. A silent shadow crossing a red star every 33 days, hiding a secret we had no way of reading. Until 2021, when a Cambridge astronomer named Niku Madhusudan threw a radical idea onto the table that sounded like pure science fiction. What if some of these sub-Neptunes were giant ocean worlds? He called them Hycean planets, effusing the words hydrogen and ocean. The hypothesis was wild, a world wrapped in a thick, dense hydrogen sky, covered entirely by a single planet-wide ocean. No continents, no islands, no mud. Just endless water, miles deeper than any sea on Earth, going all the way around the globe. And the kicker was that a Hyson world could be completely habitable. Beneath that heavy hydrogen ceiling, inside that infinite sea, something could be alive. Not intelligent civilizations, but something much closer to the invisible microbes that filled Earth's oceans for the first 3 billion years of our history. Madhusudan argued that K2-18b was the textbook candidate. It was a beautiful theory, sure, but a theory without data is just noise. To know what that air actually smelled like 124 light years away, you needed a machine that didn't even exist yet. And in 2022, that machine finally opened its eye in the dark. Think about the sheer scale of what we are doing here. We can't fly there. With our fastest spacecraft, it would take more than 2 million years of travel to hit K2-18b. We will never touch it. We will never see it as anything more than a dark pixel. Yet we can literally taste and smell its atmosphere from our couches. The physics behind it are mind-blowing. When K2-18b passes in front of its star, a tiny fraction of that starlight doesn't come straight to us. It filters right through the thin shell of atmosphere wrapped around the planet's edge. As that light passes through the alien air, the specific gases swallow up very specific colors of the spectrum, particular wavelength. So every single molecule on the periodic table leaves a totally unique barcode behind. Water steals one set of colors, methane takes another, carbon dioxide takes another. When that ray of light finally hits our detector, the missing colors act as a chemical fingerprint of a world we will never see. This technique is called transmission spectroscopy, and the James Webb Space Telescope, floating 1 million miles away in the vacuum, is the absolute pinnacle of human engineering designed to do it. In 2023, the James Webb turned its massive mirrors toward K2-18b and read its air for the first time. The results sent shockwaves through the community. Webb found methane, and it found carbon dioxide. More importantly, it didn't find a single trace of ammonia or carbon monoxide. That exact chemical lack is precisely what you would expect if you had a vast global ocean down there absorbing those gases under a hydrogen sky. It was the first hard data proving the Hysian world theory might be completely real. But buried deep inside that 2023 data stream was something else. A faint whisper in the static of the machine. A tiny blip pointing to a fourth molecule, one that would turn the world upside down if it was confirmed. Dimethyl sulfide, or DMS. And on Earth, DMS is manufactured by only one thing: life. If you have ever stood on a beach and smelled that very specific, sharp, salty, slightly sulfurous ocean tang, you have smelled dimethyl sulfide. It is the chemical exhaust of phytoplankton, trillions of microscopic marine algae pumping it into the air every single day. In nature, there is no viable geological way to make DMS in large quantities without biology. No volcano spikes it like that. No ordinary lifeless chemical reaction manufactures it from nothing. Where you find DMS, you find living tissue. Think about what that implies. For billions of years, Earth was a quiet planet inhabited solely by invisible microbes. If an alien had pointed a telescope at us 3 billion years ago, they wouldn't have seen lights or infrastructure, but they would have detected the chemical footprint of life altering the air. That is exactly what K2-18b was promising. An ocean full of invisible biology, quietly breathing into its own sky. The light we were analyzing had left that planet before the rise of the Roman Empire, crossing the void to collide with the mirrors of the James Webb. In 2023, and the signal was way too faint to call, just a valid reason to go back and double-check. So they looked again with everything they had, and in April of 2025, the Cambridge team dropped the heavy news. Madhusudan stood before the press. This time, his team had targeted a completely different instrument on the Webb telescope, checking an entirely independent range of light to cross-verify the data. And the signal of the dimethyl sulfide, he announced, was back. It was stronger than before, and it was accompanied by its chemical cousin, dimethyl disulfide, another pure byproduct of biology on Earth. The astronomer picked his words carefully, but the headline hit like an artillery shell. He called it the strongest evidence yet of possible life beyond our solar system. The world went into overdrive. Front pages, breaking news bulletins, or viral threads. For a few nights in April of 2025, hundreds of millions of people went to sleep staring at the ceiling with the exact same thought. We are not alone. That's the epic part of the story that everyone caught on their feeds. But that is not where the tape ends. That is where the brutal reality of science actually begins. Because the moment that study went public, laboratories all over the globe grabbed the exact same raw numbers from the telescope and started asking a much harder question. Are we actually looking at alien life, or do we just want it so bad that we're seeing ghosts? The first massive red flag was the confidence level. In real science, you don't get to claim a historic milestone just because the graphs lean the way you want them to. You need overwhelming, airtight proof. And physicists use a scale called sigma. A 3 sigma result means there is a 0.3% chance that the data is a total fluke, a random hiccup from the machine. That sounds incredibly safe to a layman, but for a discovery that rewrites human history. 3 sigma is a dangerous gamble. The gold standard for a definitive discovery is 5 sigma, where the odds of being wrong are less than 1 in a million. The Cambridge find locked in at 3 sigma, enough to get scientists excited, but nowhere near enough to announce you found neighbors in the galaxy. Then came the second hachazo, and this one sliced deep. A team at the University of Chicago, led by Raphael Luque, dragged the Webb data back into the lab and reanalyzed it from scratch, not to sabotage the find, but to audit it. What they found was devastating. That exact peak in the light graph that was supposed to be the signature of alien life could be explained just as well, and actually slightly better, by a completely dead, lifeless molecule, ethane, or propine. Completely ordinary hydrocarbons that form on brain-dead space rocks without a single cell of biology involved. It turned out the chemical fingerprint wasn't unique to alien microalgae. A boring, sterile gas left the exact same scar on the spectrum. But the real execution blow was the third one, the most technical and damning audit of all. A team backed by Johns Hopkins and NASA investigated exactly how the raw telescope files had been processed. The mid-infrared instrument on the James Webb is a hypersensitive masterpiece, but they found a massive vulnerability. Depending entirely on how you sliced up the raw data and how you grouped the wavelengths on your software, the answer flipped completely. If you processed the data one way, the signature of life popped up. If you grouped the frequencies using a slightly different tweak, the gas disappeared entirely. When they ran the absolute cleanest, most meticulous data cleaning methods, the dimethyl sulfide signal vanished in 90% of their trials. The NASA conclusion was a cold bouffeton. The signal wasn't coming from the planet at all. It was coming from the telescope itself. It was random instrumental noise, static from the hardware dressed up in the shape of biology. They titled their paper with absolute zero anesthesia. K2-18b does not meet the standards of evidence for life. And the genius of that audit wasn't just proving the math was wrong. They exposed exactly how the mirage was born. The infrared detector on the telescope has tiny, inherent physical quirks, built-in ticks of the technology that create data patterns out of nothing. When you clean that data on a computer, humans have to make technical choices on how to smooth out the jagged graph